Now, 2 years ago, we started our first real effort to introduce the idea of biorobotics in our BioVision meetings. And last time, we dealt mostly with mind-machine or human-machine interaction, and we had 5 distinguished researchers who reported on all of that, everything from doing exact Geminoids, people who look exactly, robots that look exactly like the same person, from Japan, to robots designed to mimic animals, to people working on trying to read thoughts through electrodes and passing them with monkeys and robots across the world. We had many interesting things to say, and one of those very interesting people will be with us in the next session as well, linking from last time, Kevin Warwick, who's the rightly named the first human cyborg because of the embedded item in his arm, and we'll be hearing more about that. But something I was missing from last year, in people who saw the little Nao dancing around, was what about robots, and what about their behaviors, and how are they going to be linked or not linked to humans in the future? Well, this is one of the things we'll be discussing in this session, and I'm very honored to introduce this first session 3 very distinguished speakers. Ronald Arkin, who's the Regents Professor and Associate Dean of Research and Space Planning at Georgia Tech in Atlanta, Georgia. And he will be our first speaker today. I mean, I can read all the CVs, but you have them already distributed. Muhammad, Marwa, they are in everybody's packages. So rather than my reading all the degrees and honors, we are very proud to have such distinguished people with us. And he will be followed by Professor Yoshihiko Nakamura, who's a professor in the Department of Mechanoinformatics at the University of Tokyo in Japan. And then Eduardo Sinibaldi, the team leader at IIT Center for Microbiorobotics in Italy. Each of them will have a presentation. I hope that at the end of it, we'll have a few minutes to ask some questions, but if not, I will re-invite them at the next session so that we have questions and interactions at that time. Hopefully we'll have enough time, but it's more important than anything else is to listen to them. So without further ado, please join me in welcoming Professor Ronald Arkin.
I want to thank you for the kind invitation to the Bibliotheca Alexandrina. This is a very important topic, and one that I've been spending a lot of time on lately, which deals with the impact of robots on the future of mankind. Much of this has to deal with the ethical issues associated with different potential applications of these systems. I could be talking about some of the things you'll be hearing about later, such as companion robots or surgical robots. A variety of different things where ethical issues start to come to the fore. But what I will be talking about today is more military applications of these systems and the ethical questions and issues surrounding them, and how they can potentially be addressed. I would say this, first and foremost, that I will talk a little bit about my research in this area, but the international discussion that this research has generated is as important, if not more important, and I am happy to be here to share this with you. What I will try and show you, which you may have figured out by now anyway, is that autonomous robots and lethal autonomous systems are coming soon to your neighborhood, so to speak. They already have lethal force. They will become more autonomous in the future, and I will share with you again why I believe that this is an important issue that we need to discuss internationally. I will also point out, as you probably are well aware of, but don't necessarily want to think about, is how mankind consistently fails in upholding battlefield ethics as prescribed by international humanitarian law. And finally, I will talk a little bit about my research agenda, which was funded by the Army Research Office in the United States. I should preface this with all my work is unclassified. I can talk freely about anything that I do with you in any respect, so don't hesitate to ask me hard questions if you like. And if I know the answer, I'll be glad to share that with you. I should share also this notion that I'm not trying to convince you that war is a good thing. It is not, under any set of circumstances. War is one of the worst possible things that humanity engages in. But the trouble is, we have engaged it since time immemorial, since the beginning of recorded history, from the Greco-Roman era, and even earlier than that. So, if you can figure out a way to end mankind persisting in international conflict, I would be extremely happy. And if you can continue to do that and pursue that, please do so. But there's another question, and this actually speaks to what's referred to as just war theory. Not only when is it appropriate to go into a war, but if you are in a war, what is the appropriate way to conduct yourself with respect to preserving humanity in the battlefield? And to many people that often sounds oxymoronic. In other words, humanity in the battlefield? Well, if you look at what true inhumanity is, it becomes easy to understand. Why is the military interested in robotics? For a multiplicity of reasons. These are the mantras, if you will, of many nations, not just ours. Force multiplication. We want to be able to use fewer soldiers to do more, to avoid having a draft perhaps, or to just increase the overall effectiveness in the battlefield. They are interested as well in fighting over larger areas with fewer forces and maintaining persistence, staying in the air for far longer than any human warfighter possibly could. We're interested in allowing an individual warfighter to see further, to act further in the battle space. And of course, all this results in a reduction in friendly casualties. But this research in particular, and my concern in particular, is not so much concerned with how we can address the issues of creating a more efficient and more effective fighting force, but rather to address the plight of the non-combatant, those innocents and civilians who are caught in the crosshairs of combat. How can we ensure, to the best as we possibly can, that we can reduce significantly, ideally eliminate, but certainly reduce the incidence of civilian casualties as this new technology is introduced. And this technology exists in so many different places and in so many different ways. It just goes on and on. These are just a few snapshots of some old, some relatively new videos of air, ground, sea systems.
Airborne.
All under development, some under development, some fielded and this is just the tip of the iceberg, basically. There are at least 50 nations developing the use of robotics technology. And I would not be surprised if Egypt was among them, developing and or using these techniques. There are many other nations deploying these systems in various stages of autonomy, mostly still human-controlled. The South Korean platform developed by Samsung Techwin is currently being deployed along the demilitarized zone between South and North Korea. It has the potential for an auto mode operation, which can engage a target without additional human intervention. The U.S. has multiple platforms. You probably are well aware of the Predator and Reaper drones that are out there, which are flown by pilots back in Nevada. A newer version is coming called the Avenger. But China has the Invisible Sword. Russia has a SCAT platform. And as I mentioned, this is the future of not just the U.S. military, but militaries worldwide. And the real question is, what does that mean? What does that mean from the introduction of robotics technology, and what should we do in terms of allowing it to escape from the laboratories into the military-industrial complex and beyond? This is just a list from a public report that it projects out to 2034 called the Unmanned Systems Integrated Roadmap, that shows at least 40, if I'm not mistaken, different systems that have potential lethal force. They're so-called force-bearing systems. Some are under development, some are actually fielded. There are, in that report, the questions associated with the issue of autonomy, when these systems and if these systems will ever be given the choice to take human life by themselves without further additional human intervention. Note that statement there. The decision to fire will not likely be fully automated until legal rules of engagement and safety concerns have all been thoroughly examined and resolved, which is the right thing to do at one level, but the other level is it appropriate? And I ask you as a community, I'm not going to tell you what's right or wrong in this. I'm going to tell you what can or cannot be in terms of both, in terms of the different types of futures, some dystopic in the way in which these systems can work. But we can have systems that go out there and take life in the future if those questions are resolved. From the Air Force, which has the boldness to try and create a projection out to 2047, I don't know many plans that have effectiveness out that long, it states that authorizing a machine to make lethal combat decisions is contingent upon political and military leaders resolving legal and ethical questions. Ethical discussions and policy decisions must take place in the near term, rather than allowing the development to take its own path apart from this critical guidance. So the armed forces in the United States are certainly aware of the potential things that could occur. And I am not a representative, I am a professor, and I just would say that having discussions not only with groups such as this, but my numerous engagements with the International Committee and the Red Cross that deals with the Geneva Conventions and many other policy-making organizations is central to coming up ideally with a consensus as to what to do with this new progress. I remember hearing the talk yesterday about progress should, to me, it seemed preceded any pace whatsoever. Well, I would say the progress should occur in a considered and guided manner to make sure that the technology that we create is used appropriately. And I do not want to put necessarily society or humanity second. Truth is important, but I do believe we have to indeed maintain our own human integrity among ourselves and even our foes. The United Nations also has been urged on multiple occasions to set up a panel on the ethics of robot weapons. The recent rapporteur said that serious concerns that have been almost entirely unexamined by human rights or humanitarian actors have been raised by this technology, and the international community urgently needs to address the legal, political, ethical, and moral implications of the development of lethal robotic technology. So this, fortunately, is well up on the radar screen among the people that need to know. But I would contend that the populations of the world need to know as well, to be able to guide the decision-making effectively. There are many secondary questions in the use of lethal force associated with humans, let alone with machines. War crime charges can occur, political fallout, the effect of morale on troops, hostility among local population, and citizen reticence towards mission accomplishment are many of these issues as well, too. So one of the questions that I ask, which is not asked too often, if at all, by technologists, is how can we effectively take charge of the situation and enhance the safety of the non-combatants who find themselves in harm's way. And I do believe, at this point in time, it's a hypothesis, falsifiable, that this kind of technology can potentially outperform humans in the battle space. And we'll talk more about that in a bit. And someone had a timer for me, but I know it's out there somewhere and I can't see it. Lethal autonomy is inevitable is the second assumption of my work. The first one deals with the notion of warfare will continue. That's an unfortunate assumption, but it's true. I do see the timer now. The other assumption is that lethal autonomy is inevitable. And why do I say that? Well, because it's already out there, and it depends to some degree on how you define autonomy. Cruise missiles. The Navy Phalanx system deployed on Aegis-class cruisers engages targets automatically, sometimes resulting in inadvertent kills, such as the Iranian airliner, which unfortunately was downed 20 years ago, I believe it was. Other examples, even with the Patriot missile, resulted in friendly fire, knocking down 2 British tornadoes in the Kuwait war. But there are many other systems, even including anti-personnel mines, which can be considered by some roboticists, including myself, as robots because they have the ability to sense, in this case through a pressure plate, and actuate through the use of explosives. More sophisticated landmines fit this category because although those are generally considered illegal due to, or immoral at the very least, due to the lack of discrimination, a hallmark characteristic of international humanitarian law, these systems have more sophisticated brothers which use seismic signatures for anti-tank or infrared signatures as well too. And so there's this discussion that I've heard ever since I was in robotics 25 to 30 years ago that deals with the notion of a human being in the loop. There will always be a human being in the loop. And at some level that's correct. But it really means where in the loop is the human? And some people argue that it should be for confirmation of every single target before it is engaged. Well, maybe. The other one is that maybe it should be at a command level, such as take a building using whatever force is necessary. There are military pressures caused by what's called the operational tempo, the need to get through an area and conduct an action in a reasonable amount of time, which is pushing more and more of this decision-making onto the robot, the so-called tip of the spear. And the only possible prevention, at least in my eyes, to do this is the use of international treaty or prohibition. And there are venues in which that could occur. There have been things like blinding lasers that have been banned even before they were introduced into the battlefield. But I am not going to argue to you that these systems should be banned. I am saying that we need to be careful about them, and I think in some ways we may be able to do better if time allows me to talk about that. So here's two rhetorical questions I throw to you. Should soldiers be robots? Don't we, to some degree, dehumanize human beings when we are training them to fight? There is a natural aversion to kill each other, yet we create this ability to kill in our and your warfighters through training. And what about the other side of the coin? Should robots be soldiers? Could they possibly act in some ways more ethically than human soldiers do? Documenting the problems of the human failings in the battlefield has resulted in one report by our Surgeon General's office. I have to give great credit to our nation to publish this particular report, which is the first formal scientific study that was ever done by returning warfighters from, in this case, Operation Iraqi Freedom from 2005 to 2007. And the numbers here were just staggering in terms of how Marines and soldiers potentially agreed to treat non-combatants under this particular set of circumstances. The potential use of torture, which is a complete violation of international humanitarian law. The unwillingness to report violations of atrocity, or the creations of atrocities. Many, many other things like this. And that's available online for you to read as well, too. I must applaud our nation for being as open as they are to share this information with anyone who is interested in it. And there's good reason, evidently, for why these war crimes exist in combat troops. And I have to say that war crimes occur in every conflict, by every side. This is not something that is unique to any particular conflict. It is everywhere. You're just hearing more of it now because of the wonderful inventions of both social media and regular media. Indeed, wars are sometimes now managed by CNN as we move forward. And I believe that many of these problems that are listed here can potentially be addressed through the use of autonomous systems. So I ask my colleagues, and in some ways I'm asking you as well too, we are biological agents that are killing each other. This is, to some respect, I guess, not different than a health issue. We treat each other with gross disrespect and dispassion in many cases in the battlefield. And do we not have a responsibility as scientists to try and find ways to reduce man's inhumanity to man through the use of technology? I argue it is. And I would say there is no easier place to do that than in the battlefield because human beings behave atrociously. Not all human beings. And I also have to preface this by saying I have the utmost respect for our young men and women who are put into the battlefield. But they are put into situations which no human being was ever designed to function in. They just break down. A significant percentage do. And that's not a surprise. And my contention is potentially robotic systems could do better. So this is the underlying research thesis for some of the work that I've forwarded. It's just a thesis. It's not an assertion. It's not an axiom. It's none of the above. It's just a research thesis. that ultimately we can create robotic systems that perform more humanely than human beings do. I don't claim that they will be perfect. I don't claim that accidents and non-combatants will not be killed. That, unfortunately, is a side product of war, and there's even in international humanitarian law, you should be aware, although I'm not a lawyer, but I know the principle of double effect, that it is not a war crime to kill a civilian. It's a war crime to intentionally kill a civilian. And there are ways in which these things can and should be measured. There's also a difference between IHL, which are the Geneva Conventions and the Hague Conventions, as well as human rights law, which are governed by the United Nations. Nonetheless, if these systems are imperfect, if they are better, if they do better than human warfighters do, the net effect is a saving of life, a saving of non-combatant lives in that. And to me, that is a humanitarian effort, if we can do better and save innocent lives through this. Obviously, the best thing is not to be in the battle space in the first place, but I don't have the technological solution to be able to address that. And why am I somewhat optimistic about that? Well, AI has been making remarkable progress in the last few years, especially even last year. I don't know if you folks have an equivalent of Jeopardy out here, which is a game for brilliant minds who recall information and almost trivia-like. We had a computer named Watson developed by IBM win that against the absolute best human champions. Brazil is also now augmenting eyeglasses for their use in the Olympics that can try and find terrorists in a crowd. And most recently, Nevada and also Oklahoma, I just learned, allows fully autonomous cars on their road. There doesn't have to be a driver on board. And Google is creating those programs, yes, the same Google as Google search engine, to try and save lives. They say that human beings, and I am completely convinced of this in Egypt, are the most dangerous thing on the road. There's no doubt about that. And so if we could eliminate the human drivers, there would be a significant reduction in casualties. So that is their motivation, which to some degree is not unlike mine. Now, The Economist when I first started this work back in 2007, kind of in a tongue-in-cheek way, caught the spirit of what I was trying to do, is to how can we ensure that these systems comply with international humanitarian law. And so the goal was basically to provide the right of refusal for a robot to engage a target. That is not always well received by the military, and in some cases in popular circles such as "I can't do that, Dave," from 2001, might also raise the hackles of some folks as well. Also, the ability to potentially report back better than other warfighters do on the unethical behavior of their fellow soldiers, and also to implement the existing laws of war. I argue that these things should be used, if used at all, under very narrow and specialized circumstances, such as interstate warfare and not in counterinsurgency, where there are high populations of civilians, such as we find ourselves embroiled in right now, in very specialized and narrow missions, such as room-clearing operations and counter-sniper operations, and also not to remove the human presence from the battlefield, but rather supplement the human presence. There's a whole bunch of reasons why I believe this is the case. The ability to act conservatively. Robots can assume far more risk on behalf of non-combatants than any human being, possibly in their right mind, would ever do. There will ultimately, with the change in the interneted battlefield, or what's called network-centric warfare, there will be more information available than any human being could possibly digest. We can keep out the emotions that make humans make mistakes, such as anger, fear, and frustration, and have them act impartially, and avoid other cognitive problems that may occur. But of course, this premise does not go unchallenged. There are many reasons as well, too, why this shouldn't occur. And even there is a group called the International Committee on Robot Arms Control, which argues against, for the immediate cessation in the use of potentially lethal autonomous systems. I could tell you more about that afterwards if you like. But there's fundamental questions from just war theory, such as establishing responsibility. The robot should never, ever be said, the robot did it, the robot created the war crime. It has to fall on either the creator of the technology, the manufacturer, the designer, the politicians who went to war using this, the military people who deployed it, and other aspects. Many, many other issues as well, too, are involved, one of which, of course, is proliferation. These things are easy to make, relatively speaking. These are not weapons of mass destruction, but they are weapons of mass havoc, conceivably, as well. But the genie's out of the bottle in many ways. So to do this, you need to represent certain things of the hallmark characteristics of the Geneva Conventions, which include establishment of a reason to act, which is referred to as military necessity. Make sure that no unnecessary suffering or superfluous injury occurs, that proportionality is adhered to make sure that you do not use more force than is required for the task at hand, and very importantly, discrimination between non-combatants and combatants, or warfighters that have become what's referred to as hors de combat, which means they have either surrendered or attained non-combatant status by virtue of wound. There's some technical stuff I'm just going to flash towards you that shows how this is accomplished. There's no time to do that. We've implemented an architecture which captures this, including components which suppress and restrict, almost in a bolt-on action, the system to make sure it complies potentially with the laws of war. A notion of an emotional system which includes an ethical adapter, which actually uses one form of emotion, which is guilt, into these systems, which, based on differentiation of pre-assessment of battle damage and post-assessment of battle damage, a change can occur in the system to prevent further use of a particular weapon system which is acting unexpectedly in the field, and stop using it because it's not acting properly. Responsibility advisor also is important to make sure that the human assumes the responsibility for the actions of these systems. There are multiple scenarios that we've described. It would take more time than I have here to be able to do that. Some dealt with the proper actions of human warfighters, such as the military about or thinking of engaging a group of Taliban at a funeral. There was a question about whether this was appropriate or not, and they did not act following the rules of engagement, which said that it was inappropriate to engage a target, including high-value military individuals in that particular location, because that's something that is inconsistent with both the laws of war and the principles of the United States. Other situations where warfighters seem to go astray include other videos of Apache helicopters under human control, potentially engaging individuals who are already wounded and unfortunately terminating them, even if they did have a potentially mortal wound. I mentioned the Korean system as well, too, that is also being currently deployed, and potential urban sniper operations as well. If you're interested in further information and seeing narrated videos of some of these scenarios, you can find them off of my website. Just look to the multimedia link, and you can find that. I do not have time to show any of them at this point. And to get to the point which I'm referring to is no short haul. We are not there yet. I'm not even sure if the military is interested in potentially doing it, although they were interested. I'm still talking to them on many, many occasions. There's many questions that remain to be answered, and there's considerable research that has to be done, particularly regarding discrimination of combatants and non-combatants in the fog of war. But ultimately, I believe that we can do better, especially after having spoken to a significant number of warfighters in terms of how things actually go down in the battlefield. So, in conclusion, I'd like to say we're not there yet. We may never be. As I said, it's a research hypothesis. One I feel warrants additional investigation. Roboticists as a collective, whether it's in this area or other aspects, humanitarian, cyborgs, take your pick, need to address the ethical issues surrounding the potential use of those questions. And there are deep ethical questions about almost everything that you will hear for the remainder of this session and all of the next session as well, too. We need to be proactive, not reactive. The ICRC, International Committee of the Red Cross, has characterized themselves once as being one war behind. We do not want to be one war behind, and I believe these kinds of things can be used in other sources. Additional information can be found in the book on the subject, and our webpage has numerous publications. I also serve on the Board of Governors of the IEEE Social Implications of Technology Society, a great place if any of your engineers out there and are not joined into that. I would encourage you to look into that further. Thank you for your time.
Thank you, Professor Arkin, and please note a question that I'm asking you, because when we come around, hopefully to get some answers either now or in the next session, I'll ask it of you. You were very dismissive in one little sentence in the middle of a busy slide that autonomous robots could run amok. And then you put between parentheses next to it, sci-fi. We all know the sci-fi movies, but the issue of giving autonomy to robots and, in addition, lethal robots really has to raise a question as to whether that is sci-fi or is it a very real risk that has to be protected against in some additional way scientifically. Anyway, we'll now move to Professor Yoshihiko Nakamura, and he, I think, will engage us further in this area of humans and machines, and what we have labeled in this particular BioVision as making the best of man and machine together. So, Professor Nakamura.
Okay. Well, thank you very much for inviting me to this prestigious conference. I'm really happy to be able to attend and talk about our work. My name is Yoshihiko Nakamura, University of Tokyo. I'm talking about humanoid and human modeling. This is a photograph I took on the street of Italy. It reminded me when I was a kid. When I was a kid, I was always scared by the car. And the car was just looking at me, always. And it's very difficult things to think about why car is looking at me. And this is another example. This is a cartoon you can find in the Alice in the Wonderland in the first edition. And this is intended for children. But this is very strange figures. It's very abstract. It's not real. I never seen rabbit like this, or I never seen human like this. Nobody thing like this. But still, it is comprehensive for children. That is a mystery. I think that is why the human beings can understand human beings. Because of that very important features, we tend to understand everything by human sense. So why so? This is a mystery. Well, as far as I understand from the literature, the mammals had to spend a very difficult time when they were born at the middle of the last ice age, and they have to cooperate each other, and they developed the performance to understand each other and help each other and predict the actions. Well, the brains had developed continuously and became larger and larger. And you know, this black part is called the proto-reptilian brains. The dinosaur has this kind of brain, and any lizard has this kind of brain. But the mammals developed the larger side, gray part or white part. And all the mammals developed this part of brain. And of course, the human beings, thank you, or great apes developed the white part at large. And what is interesting is that if you look at the textbook of the psychology or neuroscience, this is the explanation of the memory system. The memory system of humans or maybe the apes have 3 different types, like this: procedural memory, episodic memory, or semantic memory. But even the apes, birds, they have 2 kinds of memory systems. So the brain developed for the communication between each other. But still, it is not enough. If you have a lot of videos or files or music, and if our hard disk is so small, what we do is compression. The memory system is a strategy of compression. How to compress the large data set that they have to leave. That is a strategy of the memory system. So this is my preference, and I like this figure by Terence Deacon in his book. He claims that brain developed as symbol system develops. So the symbol system and language system and the brain itself co-evolved. That is the main message. So how the symbol system developed and how the symbol system helped the communication, that is a mystery of our communication between humans and other animals or mammals. And I think we have this kind of very convenient equipment in our brain. We can understand human very well. We can understand even animal in the way that we understand humans, right? So how can we use this very useful performance or gift to understand the machines? If machine is built in such a way that human can understand machines, then everybody or children or anybody can communicate with machines or robot very intuitively. So it's a perfect human interface with machines. So humanoid robot is targeting to develop this technology, to understand humans and to establish the communication between machines and humans. So the father of artificial intelligence, Marvin Minsky, in his famous book, he said, how can one make machines understand things? So the humanoid robot is targeting how one can make machines that understand humans. This is a big challenge. Well, looking at the history of human, of course, our system, the communication system, developed as the development of the brain of the mammals. But even looking at the human history, if we look at the Lucy that is found in Ethiopia, the human history goes back to the 3.2 million years ago. But some literature said that even the Neanderthal, which is 600,000 or 350,000 old, wouldn't be able to speak if they looked at the skeletal system. It should have been difficult for them to talk. And more recently, there is a very important research published, and some genes called FOXP2 has been developed around 100,000 years ago or 50,000 years ago. And that enabled humans to start the spoken languages. So the language is very short history. But before them, we have very long history of understanding the behavior based on the symbol system. So symbol system is long history and deep. And also we human use the language system. So we have been looking at this kind of problem at the humanoid robotics. And we developed, this is an example of our study. We have been developing mathematical framework to build this kind of communication framework. And this is our demonstration, what we call crystal ball. Okay, so this is being computed in real time, actually. Well, this is a video, but I took in real time. And this white person is a motion captured real-time figure. So the person is moving like this. This is a typical exercise in Japan. And we have taken this sequence of exercise as information, and we have been building the symbol system to understand this exercise. And red person is actually one segment future of this white person. So one segment is approximately 1 to 1.5 seconds. So yellow person is 2 segments ahead of time. So with this kind of the knowledge of behaviors, and we can, or computer can predict the short time future of a person. It's not mystery. By using the statistical technique or robotics technique, we can estimate human behavior like this. It's like the subway map, as the chairman showed us the other day. The sequence of the exercise is just one line of subway line. So knowing which station you are now or which station you were before, you can predict the next station. It's not mystery, right? The question is how to find out which station you are. And if you have collected a lot of data set of movement, it's like the Tokyo subway system. That there are a lot of systems. But using this, we can naturally predict the human behaviors. So we want to build the mathematically this sort of system for computer and robot. And this is the example of the data set that we've created using the nearly 20 hours motion capture data that is being offered by Carnegie Mellon University. And this black-haired-like figure is just 20% of the data set. If we show 100%, it's just a black circle. So we just showed 20%. And this is the tree structured data of 20 hours human motions. Oh, sorry. And the sequence of all of them is represented like this. This is a 20 hours motion represented like Tokyo subway network. So using this kind of data set, we try to understand human behavior. Well, not only mathematics, we actually use humanoid robot. This is the humanoid robot, and Dr. Dong-Hee Lee, she's now an assistant professor at the Technical University of Munich, is trying to teach a motion by motion capturing system. Well, the contact between human and robot is also important. So there is a lot of the real control issues, how to measure force, how to build a robot which is sensitive to the contact force. This is a hard problem of the mechanism of robot. Dr. Christian Otto is working on that. Well, this is the one example of our system. In this system, the computer is understanding Professor Lee's motion. The number you can see on the screen is the type of behavior that computer recognized from her motions. And robot is trying to synthesize his own motions, synchronized with her motions. This synchronization is very difficult. Based on the Tokyo subway network I explained, the robot can estimate the human motions. But of course, Dr. Lee does not make the completely same motions. So her hand goes to somewhere else. The robot has to go that position and make a contact. So the memory system is helpful to create the motion pattern as a reference. But more importantly, robot have to compromise with the reality, physics. So he have to find out the correct position. He have to find out the correct contact timing. These are the real physical issues for robot. Okay, so understanding the behaviors by linguistic association. So as Terence Deacon showed, we want to build the association system between the motion patterns and the linguistic system. This is more important for daily use of robot because we can talk to robot verbally. Fortunately, the natural language processing system in computers nowadays is using the statistical modeling, which is very close or very similar to what we have been using for motion computation. So the natural language processing system and motion system is naturally combined. And this is showing our system interpreting the human motions. The three sentences, unfortunately they are in Japanese, but the it's showing the first most how can I say, plausible three sentences. So the sentences are generated by motion patterns. So the most likely three sentences are presented in that way. And in other way around, from the sentence, we can create the robot motion. The sentence is something like the musician plays a violin or student do something. So actually, the computer system doesn't know this is student or musician. It's just computer probability if the sequence of words is most probable. So based on the statistical computation or probability computation, the computer system regenerate the robot motions based on from the sentences. This is our recent experiment. So this is a large humanoid robot, and there's a small humanoid robot. And this is real-time demonstration. And this is Professor Takano. And his motion is captured by Kinect system, which is very cheap, the motion capture system we developed. And three sentences, again, the sentences generated to interpret his motions. And unfortunately, Japanese, and it's not really precise. It said the person is blowing and the person is doing something, or it's hard to explain. And the quality of interpretation is not very high, unfortunately. But based on the small set of data we have created from the motion data, and we have also created the examples of linguistic interpretations. The computer system from the probability picked up the sentences like this. Students are jumping down, and a student is making a phone call now, and a person picked up, student drinks, something like this. Now we create a motion for humanoid robot. The sentence is very simple. Touch the head. And this humanoid robot, this is a small humanoid robot, and his head is being already taught. And the humanoid robot is trying to create the motion to touch his head. And the right-hand side is a reference motion created by the motion data. But it actually creates interaction, or it creates collisions. So in order to avoid the collisions, the robot have to modify the motion patterns. And computing everything, the actual robot moves like this. It's a strange motion, but this motion is created by sentence and modified to comply with the physics. Okay, so why we need this? For example, at the midday in the summer, a man visits me and enters the door, wiping the forehead with his right hand. So I can understand what he does from my motion data. This needs the motion classification. What kind of work is that? What kind of motion is that? Then I can interpret what he does by motion language association. This is what I have already explained. So the question is what I should do. I can guess what he wishes or he wants. For this, we need a linguistic inference, right? So we know he is wiping his forehead. So I might conclude that I bring a towel for him, or I take a Coca-Cola from the fridge, or I switch on the air conditioner. That can be done by linguistic association. So that is very important part why we need the linguistic system. Okay, now I'm talking about the understanding human sensation. So robotics, no sound, right? Sound? Oh, maybe my fault. Right, that's fine.
Yes.
Yeah, thank you. Let me show this sound. This is the one of the top dancer in Japan, and we have been building the computer system to estimate the muscle sensation or muscle activities. So his geometric motion and forces acting at the joint is computed. Then we estimate the muscle activities based on the force and mass distributions. So this is almost done in real time. And we can superimpose, this film is not made in real time, but the simplified system can be done in real time, and we can superimpose on top of the real image. And this is the example of the famous professional drummer in Japan. So he even claims that he doesn't use muscles. Well, what is surprising is that his center of mass is constantly set at the same point. He perfectly controls his mass distributions. So in that way, he can look at the audience, and he doesn't look at the drum system at all. And this is most recent example we have taken, and it's broadcasted a week ago in Japan. This is the Olympic athlete, the Miss Hiromi Miyake. She is the Japanese champion. And by looking at this, we can understand she uses muscles in very separately. So we also capture the other athlete who is the number 4 of the women, the weightlifting. In her case, the muscles are contracting. But in the case of this Miss Miyake, there is a little co-contractions. He's separately using the muscles. Okay, why we need this? So, again, at the midday in summer, an old man comes on the street carrying 2 bags, one in each hand. By looking at his motion with this system, we can predict which side is heavier than the other. and estimate the muscle force. And by looking at the activation of muscle force or history of muscle force, we can see his muscle fatigue. And again, based on the linguistic inference, we can decide what to do. Well, I'm a humanoid robot, by the way. I go and carry his right-hand bag, or I can bring him a chair for the rest. So combining this kind of the performance, understanding human, estimating the muscle sensation, and linguistic inference, a machine or robot can be very smart and can be supporting the human life. Okay, humanoid robot is, for me, the science for computers that understand human and the machine that support human activities. And for humanoid robot, at the same time, the information and the communication technology based on the huge data set of human motions and behavior, language, and other knowledge. So there is a lot of work in humanoid, and many people think that humanoid is a dream, and many people think humanoid is the toy world. But humanoid robot is very serious robotics field, combining the human science, human social systems, and human supporting systems for the future. And what is also very important is that the humanoid robot can go to the place where only human can go. For example, at this time, as you may know, Japan has suffering from the troubles with nuclear power plant. And going inside is very difficult. Of course, human cannot go inside. Neither robot can go because it's very hard environment. The many collapsed the building and many small things, rocks. So no robot can go into. If human can go, if there is no radiation, only human can go and climb the ladders and check everything. So human cannot go because of the radiation. Robot cannot go because of the complexity of the environment. So if humanoid is not ready yet, but if it's ready, it's a time for them to go and help us. Okay. Thank you very much.
Thank you, Professor Nakamura, for this very interesting way for your programming in linguistic inference with disambiguation and motion recognition. And it's always fascinating to me to see how far we're advancing in this field and how quickly in so many different directions. Our third last speaker in this session is Eduardo Sinibaldi, and he's involved with aerospace in some ways, but he also, I think, is going to talk to us about selected approaches and challenges in biorobotics, science, and engineering. So in order to save time, please, ladies and gentlemen, welcome Professor Eduardo Sinibaldi.
Well, first of all, I'd like to thank BVA organizer for these invitations. It's more than a privilege for me to be here for the priceless richness Bibliotheca Alexandrina represents and preciously preserved. So thank you. I'm going to present to you selected approaches and challenges in biorobotic science and engineering. And after a quick introduction, I will focus on biorobotic science by presenting the octopus as a paradigm for soft robotics, together with a new vision of plant world. Then I will switch to biorobotics engineering by presenting some challenges and, of course, opportunities from the biomedical sectors prior to concluding. So let's start from the basic taxonomy. We talk of biorobotic science when we use robotics to discover new principles by providing scientists with suitable tools and methodologies for studying biological systems. Conversely, we talk of biorobotics engineering when we use robotics to invent new solutions which could be either inspired by biological models and aimed at generic applications. Here, for instance, you can see a manipulator which is inspired by the elephant trunk, or simply applied to biological models, like in the well-known case of biomedical robotics. So as for biorobotic science, we start from a biological model, and through study, modeling, implementation, we get a robotic system which is biomimetic, that is able to replicate the biological model well enough to be used for validating scientific hypotheses on the biological model itself. And this, in general, is an iterative process ending with new scientific knowledge. While as for biorobotics engineering, we can start from a biological model and get a robotic system which is simply bio-inspired, providing new technologies and new applications for different fields, or we apply new technologies as enabled by a robotic system to a biological model. As for science, maybe it's needless to say that blind copying nature is not the winning strategy, because nature is too complex, and also because natural selection is not engineering. So, for instance, organisms that are capable of surviving are not necessarily optimal for their technical performance. Well, an amazing model for biorobotic science is provided by the octopus. Indeed, as you can see here, octopus is soft-bodied, but it effectively interacts with rigid bodies. Here you can see it is opening an oyster, and it seems bulky, but it can squeeze up to passing through very tiny passages. This is a 2-centimeter diameter hole. And moreover, they probe the environment, they reach and fetch their prey with the surgical precisions, and they exhibit a rich locomotion repertoire, for instance, by switching from crawling to swimming. And there are many features which render octopus interesting from my biorobotics point of view, including the fact that there are no rigid structure, thus allowing for a virtually infinite number of degrees of freedom, and the fact that they have a variable and controllable stiffness. Moreover, the fact that their control is distributed along the body, there are millions of neurons in each arm, allows for matchless manipulation and coordination capabilities. This renders the octopus quite a perfect paradigm for the concept of embodied intelligence, according to which adaptive behavior is not just control and computation, rather it emerges from the complex and dynamic interaction amongst the body morphology, sensory motor control, and environment. Indeed, if we take into account embodiment, many tasks becomes much easier, and this aspect is sometimes and often referred to as morphological computations. And roboticists are trying to unveil its principle by developing octopus-like robotic arms. You can see here, for instance, this walking prototype, taking into account the distribution of the muscular fibers of the real arm of the octopus, this braided structure here. And this model to achieve high controllability in their environment, and also nice soft interaction with both artificial and biological models. And all these activities are being carried out within the framework of the European project Octopus, which is coordinated by the Scuola Superiore Sant'Anna, and which aims at developing a robot which is inspired to the muscular structure, neurophysiology, and motor capabilities of the octopus. However, embodied intelligence can be studied still in octopus at a lower level by considering the octopus sucker, which represents a system per se, and we have been investigating the suckers through many techniques, including anatomic investigations and non-invasive in vivo recordings like ultrasonography, and we got some novel insights into the addition mechanism of octopus vulgaris in particular, which is achieved by a specific movement of the acetabular portion, that is the upper portion of the sucker. By the way, the studies also provide powerful cues for technological development, that is for biorobotics engineering. So we have been also studying new attachment mechanisms which are inspired by the suckers by reconstructing the real sucker up to obtaining artificial replicas. And it's worth mentioning that there is a new project, a bioengineering project, biorobotics engineering project, which stemmed from the Octopus project, and this new one is aimed at creating innovative surgical tools which are inspired by the octopus arm. Anyway, Animal Kingdom is not the only one providing a striking example of morphological computations. Plants do it as well, and do it very well. Here you can see two examples at the component level. On your left, you can see the scales of the seed-bearing pine cones, which opens in response to changes in relative humidity. And seed release is achieved by space-varying distribution of these fibers along the scale from base to tip, and most importantly, top compared to bottom. It is a hierarchical structure, and this leads to a change, a difference in the bending curvature of the upper with respect to the lower part, which in turn allows for opening. And please notice that there is no functional compartmentalization here. that this nature achieves this mechanism by an integrated design. And this is also true for the other case here, this example, where you can see the closing mechanism of the leaves of the very well-known Venus flytrap. And here triggering occurs by means of tiny hairs which are here on the top of the leaves. And this in turn leads to a variation in trigger pressure causing this snap-through mechanism. And it's worthwhile remarking that here redundant triggering is needed for the actuation to take place as a safeguard against waste of energy in trapping prey that are poor from a nutritional point of view. So in both cases, we understand that an integrated design based on multifunctionally, possibly soft materials and a hierarchical structure leads to the emergence of an adaptive intelligent behavior. And this applies to plants at a global level, at the system level as well. Indeed, plants are really interesting from a robotics point of view because they exhibit an adapted growing behavior, redundancy, high sustainability and energy efficient actuation, and a very rich sensing and coordination capabilities. Indeed, plants successfully reach their needs even without a conventional locomotion systems, and they gather information from the surroundings and combine this information with internal information and try to make decisions that reconcile both states. For most plants, in fact, the only available form of action is growth, and this involves a change in both shape and size of the whole organism, and this identifies phenotypic plasticity as a form of action in plants, that is, plants' emergent behavior. In fact, plants can respond to many cues, and besides light, for instance, the root system can respond to gravity, touch cues, water concentration, chemical cues. These responses are called tropism. And what makes for an outstanding complexity is that many of the signals arrive simultaneously. Here you can see at least 15 different physicochemical parameters which are monitored by the root system, and decisions amongst often conflicting signals have to be made, and priorities must be determined based on phenotypic change. And this complexity ensures that no plant behavioral response is autonomic, that is, morphological computation comes into play again. There are many issues related to plant root system which are interesting from a robotics point of view. For instance, the actuation system, which is very efficient, it's based on an osmotic principle, the sensory system, and also the kinematics. Plants penetrate the soil by a very complex mechanism and complex movements like circumutations with auxiliary strategies like the separation of mucus for reducing the friction while penetrating. And all these combine contribute to the emergence of plants' intelligent behavior. And of course, as you understand, it's not easy to observe roots in action. We've been developing a setup for experimental observation and also new software tools for analyzing the dynamics of the tip of the roots. And we have also developed a prototype of the apex, that is the apical system of the root, based on the same principle of the biological model, that is the osmotic principle, and we successfully tested as for response to gravity and water concentration. Yet many more investigations will be carried out within this project, which is called the Planetoid Project, will be starting in 1 week time, and which is coordinated by our center. It's basically a biorobotic science project, which is aimed to develop models and testable hypotheses of partly unknown aspects of plant roots, while keeping an eye on the biorobotics engineering side, that is to develop new generation of ICT technologies for soil monitoring and explorations. Okay, let's move to the biorobotics engineering side. And here I would like to propose you three challenges issues. The first one is related to the unstructured dynamic character of the application environments. To the purpose, let me introduce this context, that is a computer-assisted surgery platform for neurosurgery in particular, assisting this instrument here, which is a probe, a flexible probe, to get to locations which are hard to be reached by rigid conventional endoscopes. And this could be used, for instance, for biopsy, for resection, for implant insertion. And you can see the conventional ingredients of the CAS platform, like a console with haptics for the surgeon, some tracking devices, basically for registration, and this robotic arm here, or better here, which support the probe. And from a functional point of view, the architecture is rather classical. So besides the patient and the surgeons, you have a control module involving a control unit and some haptics, an interventional module encompassing the robotic supporting arm and your tools, and the processing module combining preoperative data with operative data basically related to imaging. And as for the interventional module, we have been using this robot here, which is an anthropomorphic manipulator having 7 degrees of freedom. It's a lightweight robot. It's only 15 kilogram mass. And importantly, its stiffness can be controlled. This allows for a better interaction with the people in the surgical room. Indeed, besides classical tasks like teleoperation tasks you can see here, or inverse kinematics tasks like here, we are asking to follow some preoperatively defined paths with robots. The fact that you can have a soft interaction between the surgeon and the robot allows for a safer operation in the room. And this is nevertheless a prerequisite that it's necessary, but it's not sufficient, because to get to a real safe operation, you also require the support of cognitive layers like the ones Professor Nakamura showed before. And anyway, you get a feeling of how complex this application domain is already at the level of preparative imaging. Here, for instance, we have been using MRI images, co-registered and segmented, to reconstruct the brain ventricular system, that is this system here, as well the cranial subarachnoid space. And you may want to navigate your probe here after performing a tiny hole in the skull, a keyhole, through a keyhole neurosurgery. And both domains are connected to each other, and both contains the CSF, that is the cerebrospinal fluid, which is pumped towards the upper part of the skull and towards the spine. And here you can see they are connected. It's a really challenging environment. By the way, you can use this kind of morphometrical analysis not only to get a feeling of your application domain, but also to extract some specifications for the tools. For instance, through a sort of skeletonization here, you can analyze how the curvature varies along the lateral ventricles, which is important for the design of the probe. Yet the nightmare still has to come, because what you face intraoperatively is different. Because after you're even a tiny keyhole, you may have brain shift, and you do have indeed. That is, your brain is different from what you have imagined preoperatively. Moreover, it is beating, because heartbeat causes pulsation of cerebral blood flow, which in turn is coupled to the CSF flow through the parenchyma, that is the brain matter, and this renders this environment highly dynamical. And if you want to perform some kind of visualization of this environment and you don't want to resort to ionizing radiation, it may be tough, because, for instance, it's not easy to use ultrasounds because they are reflected by the skulls. So maybe you can perform some kind of US imaging through barrel probes, but they are not straightforward. So it's really challenging, and we think that a model-based approach could be used here, even if there is still much to be done. Even if there are some aspects which can be treated more easily, like, for instance, this is the CSF flow in this region, that is the upper cervical spinal region, at the junction between the spine and the brain. This is the flow rate again versus time, and this is a reconstruction of the velocity within the spinal section, that is this elliptical annulus here. And this is derived mathematically and could be used for studying some pathophysiology of the spine disease, and also for drug delivery issues, because you may want to release your drug directly within the CSF to circumvent the well-known limitations which are associated with the blood-brain barrier. Much to do. Second challenge I would like to mention is that one of mini-invasive targeted therapy. And here the scientific driver should be known, that is to locally administer therapy so as to focus therapeutic effects and enhance efficacy while reducing side effects which are related to systemic administration. And the basic approach, which by the way is not trivial, it's that one of miniaturization. And indeed there is a growing quest for miniaturization, because it nicely allows for mini-invasive approach to remote body districts. However, when districts get smaller and smaller, actuation and powering is an issue, and it's hardly viable to translate this system to tiny districts. Here, for instance, you can see a robotic capsule, which is for delivering a medicated patch through in the gastrointestinal tract. And here we use magnetic guidance, that is tiny magnets within the capsule, which responds to an external magnetic field. Typically, it is a permanent magnet, which is driven by a robotic arm. And this allows for a reduction of the energy budget, but we still need some onboard power to actuate this release mechanism here. And the mechatronic design here is not so trivial, and you understand it's not so easy to be further reduced. For instance, if you want to tackle narrower districts like in the cardiovascular system, to the purpose you may introduce a kind of refined approach allowing for some splitting or functional simplifications. And here, for instance, this is a robotic system for diagnosis and therapy in the cardiovascular system. It is aimed to atherosclerotic plaque therapy. And we have a wireless intracorporeal device which is coupled to an external platform which integrates magnetic guidance and ultrasounds both for imaging and focus therapy. And this soft tether you may see here, it has no structural function. It's just for releasing microbubbles for ultrasounds and focus therapy and robotic agents. And we've been testing this system through this hardware simulator here. You see it replicates the human cardiovascular system. It's rather complex. You can see the beating aortic arch here. And we also developed some magnetically responsive clots to study the possibility of remote manipulation of clot debris after focus therapy. And there are some promising aspects here. However, accuracy and overall controllability of the process in a clinical setup is still an open issue, and also in particular the possibility to collect and retrieve the debris. Of course, you can use this kind of magnetic link strategy to also directly drive your agents. Here, for instance, you can see a magnetic drug targeting approach. So you release your particles within a blood flow or within a bodily flow, and you use an external source to focus your therapy somewhere here. And this is done, and it is usually studied for microvessels where you have very low flow rates and no pulsatility, so it's rather an easy flow to be dealt with. However, if you want to release your agents through the miniaturized system like the ones I've shown before, you have to account for a larger system where flow rate is larger and pulsation plays a role under physiological conditions. And this opens new scenarios. For instance, here you can see reconstruction of the blood flow in a cylindrical vessel. This is not a physiological waveform, but the mean flow as well as the harmonic contents may be representative of the flow rate in larger human vessels. And you can see here that you may be able to catch some particles that are farther away from your external source while losing closer ones. This may be intuitive or maybe not. Anyhow, this must be assessed in a more quantitative and more in depth, because it has an effect on the capture efficiency, which is the most important figure of merit of these approaches. That is, we need to better study these under dynamic conditions to really assess the effects of this therapy. Okay, the last challenge, very quickly I want to propose, is the quest, takes the approach from the bottom view, that is the quest for new materials, functional, smart, responsive material. And for instance, we've been studying polymeric freestanding nanofilms, which are polymer-based films with very large area, which could be up to tens of centimeters square, and very, very thin, on the order of a few tens or hundreds of nanometers. They are incredibly flexible and yet resistant and conformable, and moreover, they can be functionalized. So seems to be a rather ideal patch for suturing. It's already been proved, and for drug delivery and tissue repair, and also for scaffolding. And the problem here is that of remote manipulation, that is remote actuations. You can see here, for instance, that they can be sucked and injected through syringes, and they can be injected and recover the shape, so this is high conformability. And we succeed to embed magnetic nanoparticles within these fields to allow for remote manipulations, which is a first step towards application in a more complex scenarios. Another class of particles we have been studying is that of boron nitride nanotubes that are structural analogs of the most famous carbon nanotubes, but they present improved chemical and physical properties. For instance, they are excellent piezoelectric properties and very good compatibility with biological system, and we've been using that particles as intracellular nanotransducers, nanovectors for drug delivery and also for regenerative medicine. So this was just a glimpse, just to mention the fact that to fully boost and enable this target therapy approach, we need to also develop novel, smarter, more functional, more responsive material bottom side. So just three take-home messages for concluding. The first one, we need new paradigms for biorobotics. And we think that it is necessary to fully unveil the embodied intelligence of biological models to be able to develop robotic platforms which are capable of interacting with the environments in an effective, adaptive, and safe way. The second message, which is more related to the biomedical field, is that the quest for science and technology convergence, that is to make science and technology's approach converge, ranging from the macro to the micro domain, by fostering miniaturization on one side, and on the other side, developing new nanoparticles, nanotube, nanoshells, functionalized carriers, and smart structure towards an integration which is credited to lead to disruptive advancement as towards better healthcare. And this is our roadmap. This is something we really believe in. The last passage, maybe it's obvious, but it's worth remarking. And by virtue of the high interdisciplinary character of these studies, we need to collaborate. We need to foster federated efforts, possibly at an international level, to disseminate scientific results and to steer our research toward effective exploitability so as to cross-fertilize scientific and technological disciplines on one side and to create consensus and get support from stakeholders on the other one. That is to pave the way for making development really happen. Because the final aim, for instance, you can see from many talks of this BioVision conference, is development that is to improve the quality of life for everybody. I beg to conclude by some acknowledgements to my colleagues at the Center for Biorobotics of the Italian Institute of Technology, which is directed by Barbara Mazzolai, and collaborators at the Biorobotic Institute of the Scuola Superiore Sant'Anna, which is directed by Professor Paolo Dario. And I've really appreciated your attention. Thank you very much. Thanks.
Thank you, Professor Sinibaldi. Thank you very much. And I saw the name of our friend Paolo Dario was with us at the last time, and I see that the work is throughout Italy, and wonderful work that it is indeed. And I want to invite everybody now to take a break. There's a coffee break, networking break, a rest break, stretching your arm break, seeing all these exercises that you did there. You can do them outside and come back here in exactly 30 minutes for the next session on biorobotics. Thank you.